Okay, this is the third video to go through worksheet 7.4. In the third video, I will go through page 5, page 6, and page 7 all together. Okay, for question 9, it is quite straightforward. By now, you should be able to decide whenever you are being asked an energy question. First, you check, can you just do formula, substitution, get the answer? Or do you need to use the box method to actually, for example, like something like this, the box method, to check how the conversion look like, and then you put the different terms together in terms of the different forms of energy. So if you look at question 9, that's actually quite straightforward. You are asked to find the kinetic energy just before braking. So the first approach that you should adopt is actually to put down the formula and check that whether there's enough information for you to do a simple substitution. So if it is possible, then no need to worry, just do it, right? So 9A, you can find it. 9B, the work done by the brakes, you are actually changing the speed of the car from 15 meter per second to 0 meter per second. So you started with a large sum of KE, and towards the end you have 0 KE. So what does it mean? It means that this work done by the brake must account for the amount of kinetic energy that you need to remove, right? So in this case, you don't even need to calculate. So one hint that you can take whether you need to do calculation is look at the question word. If you see that the question word is determined, it means that you don't really need a formula. You can just use concepts to solve it, right? And you can see over here, if you need a formula, it means that you have to calculate. Okay, so now once you know that this work done is equals to 17,000, and you want to actually find out what is the braking distance over here, you are given the braking force. So the work done is done by braking force, right? So you know your braking force, and then this work done by the brake must be also equals to the braking force multiplied by the braking distance equals to 17,000. And since you already know the braking force is 12,000, you can actually sub into here and you'll be able to find the braking distance. Now for part D for my class, all of you almost get everything correct in part 2. But for part 1, can I throw a caution? For your syllabus, you are the first batch of students that at the curriculum branch wants you to pay very close attention to this energy store versus energy transfer. So if you look at the question is asking specifically energy store. So meaning that energy store, you cannot quote thermal energy or heat transfer because these are energy from energy transfer. So I'm not sure if you can recall, maybe I take this chance to highlight this thing again. So if you recall, there is this worksheet, you will see this cube thing, cube pictures, worksheet 7.1, and you will see very specifically what are some examples of energy store and what some examples for energy transfer. So in that question, if you go and quote thermal energy or heat, you're actually referring to energy transfer and you'll be marked wrong. Why? Like I said, because the question is actually asking for energy store. So they are asking you, oh, if now I take I step on the brake, energy is going to be lost. When this energy is going to be lost, it's going to lost to some object, right? So this object, after it receive this energy, it will store this energy gain in somewhere. What is this energy? That's what they are trying to ask you. So if you look at energy stores, right, kinetic energy cannot be, right? Because your car stopped. Would it be gravitation potential energy? Not really, because the car didn't like raise in height. Elastic potential energy, well, if the car take a break, does it get squashed or stretched? Not really, right? Can it be nuclear energy? Can you break a car and then suddenly you got nuclear energy in it? Not really, right? So it means that the last possible choice is going to be your internal energy, which Now you know, right? So if you're traveling at some speed, you have kinetic energy, you brake, no kinetic energy towards the end, the kinetic energy must be transferred to some other objects. So there's work done out, right? So this work done out will be absorbed by another object. So what will happen to this object? Well, this object can absorb this work done, store it in it as internal energy, and by now you should know that if I store it in as internal energy, my particles will move faster, and so the temperature of the object will rise, right? And if you look closely at the question, you will see that they actually give you a hint. It is found that the temperature of the brake rise. If the temperature of the brake rise, what is it trying to tell you is that the internal energy of the object must rise. So down here, they are giving you a direct hint that this internal energy must increase, right? And you know that this internal energy is a form of energy store. So actually the correct answer should be your internal energy. Alright. Okay, for part 2, my whole class got it correct. So what I'm doing is I'm just showing you case 1 where I don't consider there's any energy loss. There's no internal energy rise. So you will see that the loss of kinetic energy must be equals to the work done on the brake, and so you have this. And in the second case, I consider that there is an internal energy rise. So you will see that there's this additional term, and just by looking at the mathematics, you will see that eventually the braking distance in case 1 will be longer, and the braking distance in case 2 will be shorter. So for those of you who got it wrong, what I suggest you to do, sub some dummy values into it, and you'll be able to see the difference. Okay, for question 10, it is pretty straightforward, so I'm going to be going pretty fast. What you need to be mindful here is that the mass that is given is actually not in SI unit. So when you are substituting it to find the kinetic energy, you need to be mindful to change it into kilogram. And for part B, I just want to check how many of you read the question thoroughly. So here you can see that when the bullet actually transfer the energy into the block, only 20% of the energy is transferred, meaning that only 20% of this 500 joules has been transferred to the block. So only 80%, sorry, 20% is converted into heat. So only 80% is transferred to the block. So because of that, you will need this term, 80% of what you have found in part A is being transferred to the block, which will then raise to a certain height, meaning that there is a gain in GPE. Now, one more thing about this, when I check whether you are reading the question, is that many of you didn't read this part, that the wooden block and the bullet actually get embedded. Embedded means the bullet gets stuck in the block. So because of that, the total mass of the block has to actually include the mass of the bullet, right? So if you do it correctly, you will get this formula, you will get this answer 530. Okay, then this is question 7. Question 7 is actually quite straightforward. I'm checking the same thing, whether you are aware of the mass not being given as SI unit. So to solve 11a, you can just take the kinetic energy formula, sub into it, and you'll be able to find the answer. Here I apologize. I think I forget to upload the latest version. So this 15 meter from the ground is actually not really correct. What I'm trying to say is that it is 15 meters from where it was kicked, right? So this 15 meter is the pure gain in height. So this is the 15 meter, and to think about it, 15 meter is actually quite high. The boy has to kick the ball 5-story height. So in Singapore, 1 story is about 3 meter. You can just memorize that. So here, although as ridiculous as it is, many of you still attempt the question. Thank you very much. And to solve it is quite straightforward. You just need to apply mgh. Just remember the mass here must be converted into a kilogram. Okay, for part C, it is kind of interesting because in your chapter 2 kinematic, we say that when an object reaches maximum height, most of it is v equals to 0. but in this case it is not, right? You will find that if you apply the energy expression, you can actually see that the ball started off with a very high kinetic energy. Then after that, the ball will gain GPE, right, as it gain height. Then you would ask the question, you mean there is still kinetic energy here? And the answer is yes, because in this case we call this a two-dimensional motion. The ball is not only moving upward, right? The ball is also moving forward. So at the highest point, so what happened is that the vertical component of the velocity, it is equals to 0. But because the ball is also moving forward, so let me pick the correct color. Because the ball is also moving forward, there is actually this forward velocity. So this forward velocity is the one that will give that will give the kinetic energy at the highest point. Okay, but don't worry, this two-dimensional kind of motion where you have the vertical velocity and the forward velocity is not really in your syllabus. Okay, you will learn that in your